Hey folks, it's time for another video on linear algebra. In this one, we're going to talk about the characteristic matrix. Let A and B be real n by n matrices, that is, matrices whose entries are real numbers. Since real numbers are complex numbers, we can view A and B as complex matrices. Suppose that A and B are similar over the complex numbers. This means, by definition, that there's an invertible complex matrix P taking B to A under conjugation. Is it necessarily true that A and B are similar over the real numbers? That is, can we find an invertible real matrix P taking B to A under conjugation? The answer is not at all obvious. Multiplication with complex numbers affords new possibilities. For example, squares of complex numbers can be negative, suggesting that the answer to the question might be no. On the other hand, it's difficult to find a counterexample. To answer this question, we're going to need to dive deeper into linear algebra. We'll find the answer, and much more in this video, by unlocking the secrets of the characteristic matrix. Let F be an arbitrary field, and let A be an n by n matrix over F. The characteristic matrix of A is the matrix xi minus A, where x is an indeterminate and I is the n by n identity matrix over F. Note the characteristic matrix is a polynomial matrix, that is, a matrix whose entries are polynomials in the ring Fx. However, it can also be viewed as a matrix polynomial, that is, a polynomial with matrix coefficients. The coefficient matrices have their entries in F, so are sometimes called scalar matrices to distinguish them from polynomial matrices. Both of these perspectives are important, and both will be used in this video. The characteristic matrix should hopefully be familiar to you from the characteristic polynomial. The roots of the characteristic polynomial are the eigenvalues of the matrix. If, and only if, the matrix has enough eigenvectors corresponding to those eigenvalues, it's diagonalizable, meaning it's similar to a diagonal matrix. That's the simplest possible form of a matrix. However, the matrix may not have enough eigenvectors. Fortunately, we can still find other reasonably simple canonical forms for the matrix using its characteristic matrix. To see how, we first recall the concept of a module, which is a generalization of the concept of a vector space and will be useful in our study. Let R be a commutative ring. An R module is a set together with operations of addition and scalar multiplication by elements of R, which satisfies the usual axioms for a vector space, meaning it's a commutative group under addition and has associative, unital, and distributive scalar multiplication by elements of R. Importantly, we're not assuming that we can divide by non-zero elements in R. If we can, then R is a field, and an R module is just a vector space. A submodule is defined in the obvious way, and so is a homomorphism. Now, our matrix A acts on the vector space Fn by multiplication. In this video, we view the elements of Fn as n by 1 column vectors, and multiply them on the left by A. Importantly, this induces an Fx module structure on Fn, where the scalars in F, viewed as constant polynomials, act as usual, and the indeterminate x acts as A. More generally, if P is a polynomial in X, then in this module P of x times a vector V is P of A times V, where P of A is the result of substituting the matrix A for the indeterminate x in P. We write this module as Fna to highlight the dependence on A. As a reminder, if P of x is the polynomial seen here, then P of A is the matrix seen here, where the powers of A are powers under composition. The module Fna is finitely generated over the ring Fx, for example by the standard basis vectors over F. These vectors don't form a basis for the module over Fx because they're not linearly independent over Fx, but they still span. A submodule of Fna is just an A invariant subspace of Fn, as you can verify. And a module homomorphism from Fna to Fnb, where B is another n by n matrix over F, is just a linear transformation of the vector space Fn which intertwines A and B in the sense seen here, as you can also verify. It follows that a module isomorphism between Fna and Fnb is just a vector space automorphism of Fn witnessing similarity between A and B. So the structure of the module Fna reflects the structure of the matrix A. We can describe the structure of finitely generated modules over sufficiently nice rings using presentations. Again, let R be a commutative ring, and let M be an R module. A presentation for M is a sequence of homomorphisms as seen here, which is called an exact sequence because the image of each homomorphism in the sequence is equal to the kernel of the next. In particular, pi is surjective because its image is the kernel of the zero map on M, which is all of M. By the first isomorphism theorem for modules, which generalizes the theorem for vector spaces, this means M is isomorphic to the quotient module of Rm by the kernel of pi. By exactness, that's just the quotient of Rm by the image of phi, which is called the cokernel of phi. Let's see how to think about this thing. In this presentation of M, pi picks out M generators for M, namely the images of the standard basis vectors in Rm. These generators don't usually form a basis for M since they usually satisfy non-trivial linear relations over R. The structure of M is completely determined by those relations. But to know the structure, we don't need to know all the relations, just a generating subset of them, relations from which all others are a consequence. Phi picks out n such generating relations, namely the images of the standard basis vectors in Rn. To see this, recall that in the presentation, M is the quotient of Rm by the image of phi. Forming a quotient always amounts to imposing relations, in this case those in the image of phi. But the image of phi is just the span of the images of the standard basis vectors in Rn. Those are the generating relations. In this presentation, the structure of M is completely determined by phi, which is convenient because phi can be given by an M by n matrix over R, called a presentation matrix. This is just like the matrix of a linear map between vector spaces, except it's for a homomorphism between modules. The generating relations are encoded in the columns of the presentation matrix. Let's look at a simple example to illustrate things. The Z module Z2 plus Z3 is presented by the 2x2 matrix seen here. That's because Z modules are just commutative groups, and as such a group written additively, Z2 plus Z3 is generated by two generators, say A and B, where 2 times A equals 0 and 3 times B equals 0. All other relations among A and B can be derived from these two relations. In the presentation matrix, the first row corresponds to A, and the second row corresponds to B. The first column encodes the relation 2 times A equals 0, and the second column encodes the relation 3 times B equals 0. You should pause the video to make sure you fully understand this example. As another example, observe that the 0 module is presented by any invertible matrix of any size. While trivial, this example shows that presentations are not at all unique. Different generators and relations may present the same or isomorphic modules. On that note, consider two presentations related by isomorphisms as in this diagram. In this diagram, the presented modules are isomorphic. The proof is trivial, so I leave it to you. Intuitively, the isomorphisms between the presentations just represent changes of bases in Rn and Rm, which don't change the structure of the presented module. We say that phi and psi give equivalent presentations, and that the cokernel operation respects equivalence. We can also talk about equivalence of presentation matrices, and we'll do so later in this video. Similarly, the cokernel operation respects direct sums. The cokernel of a direct sum is isomorphic to a direct sum of cokernels. Here's what the diagram looks like. As soon as we've drawn the diagram, we've proved the proposition, because we immediately see that the direct sum of two exact sequences is exact. For the matrix A, the module Fna is finitely generated over Fx, as we noted previously, and Fx is a nice enough ring. So the natural question is, how can we present Fna? It turns out that the characteristic matrix of A is a presentation matrix for Fna. Here's the presentation diagram. Note the second homomorphism maps standard generators to standard generators. This means that Fna is isomorphic to the cokernel of the characteristic matrix of A. Informally, this theorem says that a characteristic matrix fully characterizes the structure of a matrix. It encodes much more information than just eigenvalues. Since this is the central theorem of this video, we're going to prove it. We need to show that the relations in the columns of the characteristic matrix are generating relations for the module. First, the relations in the columns hold in Fna because in that module, xi minus a equals ai minus a, which equals a minus a, which equals the zero matrix. Viewers who've seen my video on the Cayley-Hamilton theorem might be skeptical of this reasoning, because it looks a lot like the fallacious reasoning I talked about in that video, which conflates scalar multiplication by x with matrix multiplication by a. However, it's not fallacious reasoning in this context, because in the module Fna, scalar multiplication by x is matrix multiplication by a. More explicitly, the jth column of the characteristic matrix is xej minus aj, where ej is the jth standard generator and aj is the jth column of A. And in Fna, xej minus aj equals aej minus aj, which equals aj minus aj, which equals the zero vector. The argument above just shows this for all columns at once. Now we need to show that these relations generate all relations in Fna. To this end, suppose Px is an arbitrary relation which holds in Fna. Note Px is a polynomial vector, a vector whose entries are polynomials in X. However, viewing it as a vector polynomial, a polynomial with vector coefficients, and viewing the characteristic matrix as a matrix polynomial, using division with remainder we can write Px as xi minus a times a quotient qx plus a remainder r, where qx is also a vector polynomial and r is a scalar vector. Recall that we're viewing the vectors here as column vectors, so the multiplication of matrix and vector coefficients makes sense in the order written, and the division algorithm works as usual. Now, we know from the first part of the proof that xi minus a times qx is a relation which holds in Fna. Here we return to viewing xi minus a as a polynomial matrix, and qx as a polynomial vector, so that the product is a linear combination of the columns of the characteristic matrix over the polynomial ring Fx. Since the columns are relations which hold in Fna, so is the linear combination. It follows that the scalar vector r is a relation which holds in Fna, which is only possible if r is the zero vector. But that means Px is in the span of the columns of the characteristic matrix, so the columns are generating relations as desired. In fact, the columns form a basis for the relations, but we won't need that additional detail. It follows from this theorem and the proposition about equivalent presentations that matrices over a field are similar if and only if their characteristic matrices are equivalent. At first glance, it might seem like we've only reduced the problem of similarity for scalar matrices to a harder problem of equivalence for polynomial matrices. But the equivalence problem is tractable. We have another theorem. The characteristic matrix of A is equivalent to a unique diagonal matrix in which the diagonal entries are monic polynomials, each dividing the next. Notationally here, I'm using square brackets to denote the 1x1 matrix blocks down the diagonal. This matrix is called the Smith normal form of the characteristic matrix. It's useful because two characteristic matrices are equivalent if and only if they have the same Smith normal form. The polynomials themselves are called the invariant factors of A, and will be denoted like this to highlight the dependence on A. Note some authors call them the similarity invariants of A, or call them the invariant factors of the characteristic matrix of A. In any case, the existence of the Smith normal form can be proved through the Smith algorithm, which uses polynomial division with remainder and elementary row and column operations on the characteristic matrix. I'm not going to go through the details of this algorithm here because it's a little tedious, and that's what computers are for. You can easily compute examples using your favorite computer algebra system. The uniqueness of the Smith normal form will be seen later in this video. Now, at this point we know that matrices over a field are similar if and only if their characteristic matrices are equivalent, which is true if and only if those characteristic matrices have the same Smith normal form. It follows that the matrices are similar if and only if they have the same invariant factors. This means that invariant factors form a complete set of invariants for similarity, hence their name. Since the Smith algorithm allows us to effectively compute invariant factors, it allows us to effectively decide similarity, which is cool. It also allows us to effectively decompose a matrix. To see this, first recall that the module Fna is isomorphic to the co-kernel of the characteristic matrix of A. Since the characteristic matrix is equivalent to its Smith normal form, and the co-kernel operation respects equivalence, this is isomorphic to the co-kernel of the Smith normal form. And since the co-kernel operation also respects direct sums, This is isomorphic to the direct sum of the cokernels of the 1-by-1 matrices containing the invariant factors of A. This is called the invariant factor decomposition of the module Fna. To extract insight from it, we need to better understand those cokernels. For f a polynomial, monic of degree d, what is the cokernel of the 1-by-1 matrix containing f? Here's a presentation diagram. The 1-by-1 matrix containing f takes the module fx into itself, and its image is the submodule generated by the polynomial f, which we'll denote by parentheses. By the first isomorphism theorem for modules, the presented module must be isomorphic to the quotient module of fx by the submodule generated by the polynomial f. We now study this structure. It's easy to see using polynomial division with remainder that the projections of the powers of x up to d-1 generate the quotient module, and in fact form a basis for it as a vector space over the field f. Here we restrict scalar multiplication to the field f to make the module a vector space. It's also easy to see that the matrix of x with respect to this basis looks like this, where the entries in the last column come from the coefficients of the polynomial f. This is called the companion matrix of f, denoted C of f, or just C for short. Notice C is a d by d matrix, so it acts on the vector space fd. If f is the constant polynomial 1, then d is 0, and the companion matrix is the empty matrix. It follows that the presented module is fdc, which is called a cyclic module since it's generated by powers of c. More specifically, if we look at the columns of C, we see that the image of the first standard basis vector in fd under powers of c is the standard basis for fd. We can also extract additional information from the quotient space. It's easy to see that the minimal polynomial of the projection of x is just f. Recall by definition the minimal polynomial is the monic polynomial of least degree, which kills the thing. It follows that the minimal polynomial of the companion matrix of f is f. And a quick determinant computation shows that the characteristic polynomial is also f. A matrix whose minimal and characteristic polynomials are equal is called non-derogatory. You're free to make derogatory remarks about other matrices. Returning to the invariant factor decomposition, we now see that it can be rewritten like this. We also see that it's a cyclic decomposition, since each of the submodules in it is cyclic. Recalling that these submodules of Fna are A-invariant subspaces of Fn, we can translate this into the language of matrices. We obtain that A is similar to a block diagonal matrix in which the diagonal blocks are the companion matrices of the invariant factors of A. Some of these companion matrices may be empty. This normal form was known to Frobenius. It's often called the invariant factor version of the rational canonical form. The word rational appears because the form can be computed using arithmetic operations over the base field. In fact, a change of basis matrix witnessing the similarity can be computed from the Smith algorithm, but again, we'll leave that to the computer. This normal form is extremely useful because it always exists for any square matrix over any field, and it lets us reduce many problems about square matrices to the corresponding problems for companion matrices, which are simpler. We can also read many structural properties off of the normal form. For example, since the minimal polynomial of a direct sum is the least common multiple of the minimal polynomials of the summands, it follows that the minimal polynomial of A is the invariant factor of highest degree. And since the characteristic polynomial of a direct sum is the product of the characteristic polynomials of the summands, it follows that the characteristic polynomial of A is the product of the invariant factors. It's now immediate that the minimal polynomial divides the characteristic polynomial, which gives us another proof of Cayley-Hamilton. And in fact, the minimal and characteristic polynomials have the same prime factors and same roots, namely the eigenvalues of the matrix. But of course, the multiplicities may differ. The uniqueness of the Smith normal form has another important consequence. Namely, the invariant factors of a matrix are also invariant under field extension. Why is this? Well, a Smith normal form over the base field remains a Smith normal form over the extension field. And since there's only one over the extension field, it's the same one. So the invariant factors are the same. Since the invariant factors form a complete set of invariants for similarity, this means that if K is an extension field of F, then matrices over F are similar over F if and only if they're similar over K. In particular, if the matrices are similar over any field, they're already similar over the smallest field containing the entries of the matrices. This is a remarkable result, which answers the question posed at the beginning of this video in the affirmative. Real matrices, which are similar as complex matrices, are also similar as real matrices. We can describe the invariant factors in another important way, which gives us even more insight using determinants. Again, A is an n by n matrix over the field F. The kth determinantal divisor of A is the greatest common divisor of the kth order minor determinants of the characteristic matrix of A. This definition makes sense since the kth order minors of the characteristic matrix are polynomials over F, which have a greatest common divisor. We take that greatest common divisor to be monic. It's denoted like this, again to highlight the dependence on A. We can prove that the kth determinantal divisor is just the product of the first k invariant factors. This generalizes the result we saw earlier about the characteristic polynomial, which is obtained by taking k equal to n. Indeed, by the Cauchy-Bonnet theorem, which I covered in prior videos, the minors of equivalent matrices are related in a way that allows us to use the Smith normal form of the characteristic matrix to compute the determinantal divisors. Since the Smith normal form is diagonal, and each diagonal entry divides the next, the result is then immediate. We can turn this result around and express the invariant factors in terms of the determinantal divisors, which shows that the invariant factors, and hence also the Smith normal form, are unique. We also obtain the corollary that matrices over a field are similar if and only if they have the same determinantal divisors. Since the determinant is invariant under transposition, we obtain the striking corollary that every square matrix over a field is similar to its transpose. This is a very deep and beautiful result. In a prior video on duality, I talked about the close relationship between a matrix and its transpose, but this result takes us farther. In conclusion, I want to reiterate that the characteristic matrix encodes much more information than just eigenvalues. As we've seen, it holds all the secrets to the structure of a matrix. And there's much more we can do beyond what I covered in this video. If you're interested in seeing more, please let me know in the comments. Here are the references I used while making this video. As always, thanks for watching.